Welcome back, everyone. We are going to finish up our discussion of truth tables. So last time we left off talking about how we can use truth tables to classify or to categorize statements in propositional logic. And we classified them into three different types. Statements that are logically true. They're necessarily true. They can't be false. These are tautologies. They are tautologies. They're statements that can never be wrong. But a lot of times they are, while they are true necessarily, they are trivially true. So for instance, if I said all flowers are flowers or all squares are squares, okay, that can't be wrong, but it's not particularly interesting. And if you were to negate a tautology, that would make it a self-contradictory statement. So if you were to say it's wrong to say, or it's false that all A's are A's, all flowers are flowers, you would be contradicting yourself. Most statements that we come across in an everyday sense are contingent, which means that whether or not they're true depends on how the world shows up. So the statement, I'm wearing blue jeans. Well, I'm not wearing blue jeans right now, so it happens to be false. But before you know it, I'm sure I'll be wearing, at least jeans, if not blue jeans. So that's a contingent statement. And we practice this in section 6.3, Roman numeral number 1. So we're going to start this part 2 of this lecture on truth tables is we are going to compare statements. When we classified statements, we were looking at individual statements and then categorize them or classifying them. But now we are going to look at least two statements and see if they are consistent or if they contradict each other or if they are logically the same or if they're inconsistent. I think if we jump right into the practice, that's the best way to explain these different kinds of relations. So I will come back here and talk through each of these more general definitions. But let's go to 6.3 Roman numeral number 2. And we're right here. So in number 1, we are comparing this statement, not D or B, with this one, not D and not B. Now, can you tell just by hearing that, listening to that, or looking at these two statements, whether or not they are the same or consistent or logically inconsistent? You might not be able to tell. Now, I taught you about a logical theorem or a logical law called De Morgan's rule or De Morgan's law or De Morgan's theorem, named after a logician whose last name was De Morgan. And it allows us to deal with negated conjunctions or negated disjunctions, negated ands or negated ors. And essentially, we are going to, if you will, distribute this negation to both of the conjuncts as long as we change the and to the wedge. And so when we do that, we're going to end up with not D, which we have here, or, which we have here, and something very close to this. Instead of B, we're going to have not B. And we know through another rule called double negation that not B is the same as B. So I can tell you even before we do the truth table that these two statements are logically equivalent. And that's one of the things we're trying to determine in this exercise. So we're going to use truth tables to figure out. Oh, let's see if I can zoom out here. Oh, there we go. really not? I don't know what's going on here. Well, we can just read it. Use truth tables to determine whether the following pairs of symbolized statements are logically equivalent. Semantically, are they the same? Which they are, and we're going to prove that. Are they logically contradictory, consistent, or inconsistent? So first, we should check to see if they are logically the same or contradictory. And then if those relations don't apply, then we can talk about consistency. So this is what we're going to do. And this is really just not letting me zoom the way I want to zoom. Let me try. Okay, let's do this. We are going to start with our horizontal line. And what letters do you see? I see D's and B's, and we're going to put them in alphabetical order. So B first, and then, oops, and then D. And then each of the statements. So not D or B. Let's just get a little bit more room here for our table. And then over here, we're going to have not D and not B. Okay, great. So there needs to be a dot there. And I think we are good. Okay. So how many simple statements do we have, or atomic sentences or statements we have? We have 2. So that means that we need 4 rows. And the pattern is going to look like this. 2 T's, 2 F's, start with T and alternate. So let's do that. And let me try with, no, you know what? If I type it, I think it won't be as fast. Okay, so 4 rows, 2 T's, 2 F's. This should be an F. And then this is going to be, you can see that these start to look like each other a little bit, right? So let's fix that. So in some systems, instead of T's and F's, they use 1s and 0s. 1 for true, 0 for false. So if you're taking a computer science class, you might do some truth tables. And, oh, see, I'm trying to talk and do this at the same time, and I'm already messing up. And you might use 0s for false. Okay, so this is going to start with T and alternate. All right, so we might identify the main connectives of these. So we have this wedge, and you might think that this dot's the main connective, but no, it only applies within the parentheses. This is the main connective. So we are going to be focusing on these columns when we compare to see if they're logically equivalent or contradictory. Okay, so let's work on these. If D is true, false, then not D is just going to be the opposite, right? Now, so I'm kind of skipping over that step of, I could directly under D put TF, but once you start doing these, you can start to realize that you can do things much more quickly. So FT. And then B, we've done B, so we can just copy this over. TTFF. And then what's going to go in here is going to depend on these disjuncts. So remember that or statements are only false when both parts are false. Otherwise, the truth spreads to the rest of the statement. The virus of truth for disjunctions. And if it's a conjunction, which we have here, it's the virus of falseness. So you can circle this. You can erase these, the left and the right disjuncts, or just cross them out. But these are going to be true, true, and true because you have at least one T. All right. So in here, we're going to copy the D again right underneath D. And you might say, but isn't it not D? No, this parenthesis, singular parentheses, this parenthesis, left parenthesis gets in the way. So it's negating this whole conjunction. So we're going to have TFTF. And I already can do some things. This is an and statement. And I know that with conjunctions, falseness spreads like a virus. So this dot is going to be, this and is going to be false in lines or rows 2 and 4 because the left disjunct is false. Is going to be false here or here? It depends. If the right side is false, then yes. If not, it's going to be true. So not B is going to be the opposite of this. So instead of TTFF, we're going to get FFTT. Which sounds funny. FFTT. And these Fs are not coming out great, but hopefully you can make them out. And I don't even really need to do these two. So here we're going to end up with an F. Because this falseness spreads. But here we're going to end up with a T because both parts are true. Again, the English example that we started with for and statements was I'm bringing cake and ice cream. And if I say I'm bringing both, then the only way that I keep my promise is if I bring both. In these other worlds, I fail to bring the ice cream or both, or I fail to bring the cake. So now we can kind of ignore this. We can ignore this. And this negation, it's negating this and. And so the truth value underneath this outer negation is going to be the reverse or the flip of these values. And we're going to end up with this. So instead of FFTF, we're going to get TTFT. That's going to go right here. TTFT. It's like a lowercase t. And we can circle this if we want. And look, we can compare these, and they are identical. Now, you might be wondering, suppose that this had been TTTF, and you might say, well, in one sense, it's the same as this column because this one has 3 T's and an F. And if this had 3 T's and an F in a different order, would that make a difference? Could they still have the same meaning? Could they still be logically equivalent? And the answer is no. The columns underneath the main connective need to be strictly identical, row for row identical. And if so, they're logically equivalent. And if not, they are not logically equivalent. So what would it mean for two statements to be contradictory? Well, we have two statements that are contradictory. Namely, if we got rid of this negation, we would be left with D and not B. And those truth values are the opposite of these ones. Instead of TTFT, we have FFTF. So if this were a different problem, if we had gotten rid of this negation and we were just looking at D and not B, then these two statements would contradict one another. They would be contradictory statements, which again, in general, I mean, we can start to look at well, this is a little bit drawn on, but I think the part we need to, you can see contradictory here, opposite truth value on each line. So when you go line by line, instead of T, T, F, T, we have the opposite. F, F, this F turns into a T, this T turns into an F. So they, but the original statements are not contradictory. They're logically equivalent. So we are supposed to determine if these are equivalent or contradictory. So we did that. They are equivalent. And then if these relations do not apply, determine if they're consistent or inconsistent. So we don't need to do that part because one of the relations did apply. So we can go on to the next one. Great. So here, M or F and M, and neither F nor M. And again, if we play around with that De Morgan's rule that I talked about, we can sort of distribute this negation, but we have to change this wedge into an and. And so we're going to get not F and not M. Well, that looks like the contradiction of F and M. Instead of saying these are both the case, we're saying neither of those is the case. So we're going to predict that these are contradictory statements, which means that under their main connectives, we are going to see opposite truth values. Or another way to put it is for every line on the truth table, if this is true, then this will be false. And if this is false, this will be true. Okay, so we need our line here. And if you've been following along the textbook, there's another way to do these truth tables that is a little bit, let's see, it's a little bit less busy. And the table is a little bit smaller. And so some people prefer this. So let me show you that way now. So what we're going to do is usually after you draw the horizontal line, you look for what letters do you see. You mentally erase all the symbols. And you say, oh, I see F and M. And then you will put those in alphabetical order here. So we would put F here and then M. So the shorter way to do it, the way the book shows you both ways. But the alternative way, and feel free to do it this alternative way, is you just skip those simple statement columns and you just go straight into columns for the statements. So we would have F, M, and then a column for not F or M. Dot in there. And then the leftmost letter, the first letter that we see is this F. Immediately underneath that, let's try the text this time. You know what I got an idea. I'm gonna get more clever. Immediately underneath that. Ooh, okay, I need the select maybe. Oh, good, okay. Okay, so now I want to copy and paste this. Well, let me do it. No. No. Well, let's try this. So we're going to do the pattern, which is TTFF. Oh, what did I do? Oh, golly. Oh, no. Oh, geez. Oh, I hit all sorts of wrong buttons here. TTFF. See, these are getting a little bit out of order. Let's just go with it and try it. And then under the M, we'll do the second pattern, which is TFTF. So this is always the pattern for a 4-row truth table. T. F. I don't know if this is saving me much time. T. F. And we know, maybe I'll draw in between these. And we know that with an and statement, the only way it's going to be true is when both parts are true. So these are all going to be false. The falseness here spreads to the middle. So let's make these all false. And since we predicted that these are self-contradictory, we should expect to see the opposite truth values here. We should expect to see FTTT. So this is a little bit bold, but I'm going to be bold. Remember that soap opera, The Bold and the Beautiful? Probably not, but it was a show. I'm going to be bold. I don't know about beautiful, but I'm going to be bold. So instead of T, we have F. Instead of these 3 Fs, we're going to have 3 Ts. So let's hope this works out. So what goes underneath F? Well, we already did F. It's T, T, F, F. Right? T, 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 F, F. What goes under M? We already did M. It's T, F, T, F. T, T, F. Ooh, it's getting wavy. You can see it gets a little wavy. Okay. And for or statements, it's the truth that is contagious. So these are all true. We only get a false down here. And so we can ignore this now and ignore this. And this negation is going to flip the truth values underneath this wedge. And so this triple TF is going to turn into look at this. I was too bold. I was too bold. Indeed. Indeed. This triple TF is going to turn into triple FT. It's going to turn into triple FT. Oh, I guess I didn't need to delete that last T. Yeah. So our prediction was incorrect. Hey, that happens. So these are not contradictory statements because we would need to have the opposite values. We would need F triple T, and we don't have F triple T. We have triple FT, which is interesting, but not self-contradictory. So they're certainly not equivalent. They're not contradictory. So the first relations didn't apply. So we're going to see if they're consistent or inconsistent. Before we do that, I want to speak to why even I, just for a little second, was so bold to speculate that these were contradictory. Because when we do De Morgan's, this statement is going to turn into not F and not M. That's a bad negation, but so be it. Not F and not M. And it looks like, hey, look, we are negating the F and the M here. But really just the the contradiction of the statement F and M, it's not this. I'm just going to take this whole thing, put it in parentheses, F and M, put it in parentheses, and then put a negation on the outside. And then when you do De Morgan's on that, you're not going to get this. You're going to get it with the wedge. So if we either change this wedge to a dot, then it would be self-contradictory. Yeah, or if we just had this. Now, while they are not contradictory statements, they certainly are inconsistent statements. So how do we know that? How do we tell that? Well, for logical equivalence and looking for contradictions, we are comparing columns. We're comparing columns underneath the main connector, or the main operator of these statements. For consistency, we are going to look left to right horizontally at rows. Okay, so we're going to ignore everything but what I have circled here, or ovaled, if you will. And we're going to go row by row, or line by line. And what we are looking for is a row where there is truth under all the main connectives of the statements. There's only two statements here, so we're looking for a row where both statements are true. And we won't find that. In row 1, are both statements true? No, this one's true, but this one isn't. And in row 2 and 3, both statements are false, so they can't both be true. And in row 4, are they both true? No. Well, this one's true, this one isn't. And so if there's no row where both statements are true, then by definition, the two statements are logically inconsistent. So what does that mean? That means it's impossible for both statements to be true at the same time. And that's what we have proven with this truth table. There's only 4 possibilities, so it is quite literally impossible for both of these statements to be true at the same time, which means that if this statement is, it means that there's no possible world where this statement is true and this statement is true. Let me give you an English example just to really drive that point home. If I were to tell you, if I were to say 3 random things to you, like it's February, the Super Bowl is on, and we are in Utah. It's February, the Super Bowl is on, and we are in Utah. Are any of those statements true? No, at least when I made this video, it's not February. It's not the Super Bowl, and we're not in Utah. So all of those statements happen to be false. However, those 3 statements are together. Oops, I didn't mean to do it. They're together. They are consistent. Those 3 statements are consistent. So consistency doesn't mean they're actually true. It just means that it's possible. You can imagine without contradiction all of those things obtaining at the same time. So even though it's not February, it's not the Super Bowl, it's not on, and we're not in Utah, can you imagine it? Could you imagine it being February? Could you imagine it being February and the Super Bowl's on? Could you imagine it being February and the Super Bowl's on and we're all in Utah? Sure, you can imagine it. What does it mean to imagine it? It means that it could be the case. You can imagine it without contradiction. Let me give you 3 statements that are logically inconsistent. Suppose I told you that we have, okay, so I'm making this on a Tuesday. So if I were to say, here are the statements. Statement number 1, it's Tuesday. Statement number 2. Tomorrow is Friday. Statement number 3. If tomorrow is Friday, then today can't be Tuesday. I'll say this again. Today is Tuesday. Tomorrow is Friday. And then if tomorrow's Friday, then we know that tomorrow, we know that today can't be Tuesday if we grant that tomorrow is Friday, right? So those 3 statements cannot simultaneously be true because you can't even imagine that without contradiction. You would contradict yourself. What would the contradiction be? The contradiction, it would be all sorts of things. You could derive all sorts of contradictions, but the most obvious one is those 3 statements entail that it's Tuesday. Why do they entail that? Because the first statement is that it's Tuesday, but they also entail that it's not Tuesday. Why is that? Well, because if we assume that tomorrow is Friday, and we assume this next one is just true in our world, if we assume that tomorrow's being Friday means that today cannot be Tuesday, then it follows that it cannot be Tuesday. But we just said that it is Tuesday, so that's the contradiction. Okay, so for number 2, they are not equivalent nor contradictory, and they are not consistent. They are inconsistent. So by the way, if 2 statements are consistent, then of course they're not inconsistent. And if they are not consistent, then they're inconsistent. So that hopefully should be clear. Okay. Let's do this bad boy. Let's do it. Let's do it right here. So we're looking, this is the first statement, this is the second one. So we have not A, triple bar X, and I'm going to do it the shorter way again, so we can practice. X, not A, wedge, and not X. Okay, and we need an and in here, a couple ands, and we need a triple bar. Oh, you know what? I was gonna do an equal sign and then add a third line, but this is pretty good. That's fine. Okay, so we're looking at these 2 statements. So the earlier way I taught you, what we do is we would look at what letters do you see, and I see A and X, and we would put them in alphabetical order over here, and then we get their own columns. And then if we only had 1 letter, then there would be 2 rows in the table, and if we have 2, like here, there's going to be 4 rows. So under A, we are going to have 4 rows, and it's the first letter we see. So we're going to have that pattern of T, T, F, F, and X is the next letter. So that's going to get the next pattern. Again, if you're like, where do these patterns come from again? They are just arbitrarily selected to capture all of the possible truth combinations. So this is where this pattern comes from. Both statements there's 4 possibilities. Both statements are true, both statements are false, one's true and one's false, and vice versa. So that pattern is a T, F, T, F. Now, the left side of this biconditional isn't merely A, it's not A. So we need to flip these values. So this is gonna turn into FFTT. For some reason, that just tickles me a little bit. Maybe it's that TT. Makes me think of, what is that? Those characters on Star Wars, Jawas or something that kind of, they don't go TT, but they kind of go DD, I think. Maybe Jawas. They kind of DD. I'm not doing it well. I don't know. Some of you know what I'm talking about. So we can ignore this. And we're looking at a biconditional. So what are the characteristic truth table of a biconditional, that table? What does that tell us? Well, we're looking for sameness. So we have sameness in lines or rows 2 and 4. And where we have sameness, we're going to have truth. We're going to have truth here and here. Here we do not have sameness, and so we have falseness, falsity, falsehood. Still can't decide which of those three I like the best. Falsehood certainly is a word, but falsehood is something that's not true. The property of being false. Falsity. Falseness. I mean, philosophers make up words, so we can pick anything we want. So what's the main connective? This is statement 1, this is statement 2. The main connective is this triple bar. And so we are going to be focused on this column. So we don't have to look at this anymore. The danger in crossing this out is when we want to double check, it's harder to do that when you cross things out. Okay, so now we need to fill these in. So X, we already did that. See, cross it out, TF, TF. Whoop. And we know things about this conjunction. We know that when the left side is false, that spreads and infects the dot. Not A. We could do the values underneath A and then not A, but we already did not A, so it's going to be the same. So it's F, F, T, T. And we only care about the first and the third value, which is F, and then in the row 3, it's T. And so we are going to end up with a true here, because both parts are true, but the falseness of this is going to spread to the dot. And so now we can kind of ignore this, and we can kind of ignore this. And so this disjunct, this is the main connective, by the way, the main operator. The left disjunct of it has these truth values. And for the right disjunct, A, that's the TTFF pattern. And we can, because the row 3, row 1, 2, 3, or line 1, 2, 3, 4, because in line 3 and 4, this conjunction is false, the left side of the conjunction is false. The whole thing has to be false. That's the nature of conjunctions. Not X. Well, in row 1 and 2, we have TF for X, which we have here too. So not X is going to be the opposite. It's going to be FT. And the conjunction is false in row 1 because the falseness here spreads, but this has 2 truths. So that'll be true. So we don't care about this so much anymore. So we have a wedge statement, an or statement with these 4 conditions. And the only way that this is false is when both parts are false. So that happens in row 1 and row 4, right? In row 1, they're both false. And in row 4, they're both false. But in rows 2 and 3, at least one part is true. And so this disjunction will be true in that case. And then we can circle this. We don't have to, but this is common. So we're comparing these two statements. Here are the columns underneath their main connectives. And lo and behold, they are logically equivalent. The exact pattern, FTTF, FTTF. And so we did 5 there. By the way, if two statements are logically equivalent, then as long as neither of them are self-contradictions, they will be logically consistent, right? These two statements are logically consistent because there's at least one row, namely row, we can number these if you want, namely row 2 and row 3, where both statements are true. In row 2 and row 3, they're both true. And if it's possible for both statements to be true at the same time, they are logically consistent. Okay. Let's see. So that was 5 in, we are in 632, 616, 62, 63, part 2, number 5. Logically equivalent. That's like we said. Number 1, we said that they were logically equivalent. And number 2, for a second, even I thought that they were contradictory statements, but they are neither equivalent nor contradictory, but the two are inconsistent. So 2 here should say inconsistent. Yep. So good. Wonderful, wonderful. Wonderful, wonderful. Okay, so did we do all the things we want to do here? One more. So there's one more here. All right, so let's do this. This is 6, 3, right? 6, 3. Yeah, Roman numeral. Sorry for all the moving around. 6, 3, Roman numeral 3, 8. Eric Carson sums up his beliefs about God as follows. God exists if and only if either life is meaningful or the soul is not immortal. So this is sort of a double negative. Not immortal is saying that the soul is mortal, which is usually, in most religions, people tend to think of the soul as immortal. So this is kind of strange to think of it as not immortal. But okay, and so it's just saying, you think of this as the logic, this statement has a two-way street in terms of its logic. If God exists, then life is meaningful or the soul dies, essentially. And if either of these is the case, if life is meaningful or the soul dies, then God exists. Yeah, this part you could almost ignore it. God exists if and only if life is meaningful. So if life is meaningful, God exists, and if God exists, life is meaningful. You could kind of think of it as that, and then maybe add this or. That sounds kind of funny. That's the first part. God exists is the second claim, and the soul is immortal. So that's something that's going to get funny here, because if we take the first one, if we take it for granted, then this first part of this and statement is going to entail, well, we better, if the soul is immortal, that's going to negate this. So we better hope that life is meaningful, or we're going to get a contradiction. Okay, so statement 3 is, if God exists, then life is not meaningful. That's a strange statement, but that's the claim. So here's the question. Is it possible that Eric's beliefs make sense? And we're defining, in this case, making sense in terms of logical consistently. So could somebody consistently believe these 3 statements? You might guess no, but let's find out. So we can, so you might just read this and try to figure it out, but it's tough. So so what we can do is do a truth table. Let's see, maybe I'll try a new share. Let's try a whiteboard here. Okay, God exists if and only if either okay, actually I'm gonna put it here. Okay, so the text is going to be G. We have if and only if. So let's start with this and we'll add a line. Either, it's gonna be in parentheses, life is meaningful. We can do L, or the soul is not immortal, so not S. That's the first statement. The second statement is God exists and the soul is immortal. So that's S. Soul is immortal is S, because this part is soul is not immortal. And then statement 3 is an if then. It's G horseshoe, not L. Oh, oh, golly. Oh, golly, golly, golly. There we go. Okay. We need an and here. Bigger. Font. Much better. Much better. Draw. We want this blue. It's dark enough. Okay, God exists and the soul is immortal. And then we need a horseshoe and we need another line here. That's good. And then we need a horseshoe here. And then maybe even maybe just make some room. Yeah. These are our three statements. These are our three statements. Let's go through them again. God exists if and only if L, which is life is meaningful, or not S. S is the soul is immortal. So saying it's not is not S. The second statement is God exists. That's just G. And the soul is immortal, which we said was S. And the third statement is if God exists, then life is not meaningful. We said life is meaningful as L, so it's not meaningful, it has to be not L. So we're going to look at these three statements. And again, you could say, like, what letters do you see? I see G, L, S, G, L, S. And so we could put them in alphabetical order, which they are, and they could each get their own separate simple statement columns. But we'll do it the little bit of the shorter way the book kind of prefers. And so we'll have we had to put in a pattern here. And we have to figure out how many rows do we need. Well, so far we've been doing a lot of statements. We've been comparing two statements, and statements have had two simple propositions in total. But we're looking at three statements, and within them there are three simple propositions. So we need 8 lines or 8 rows, and we're going to need this pattern. So again, as you can see, as this keeps doubling, there's a rule. The leftmost column will be half T's and half F's. There's only one column here, so it's the leftmost, and it's half T's, half F's. With 4 rows, the leftmost column is half T's, half F's. Same thing with 8 rows. The leftmost column is half T's, half F's. Even with 16, the leftmost, it's half T's and half F's. 8 T's, 8 F's. A second rule of this pattern is the rightmost column will start with T and alternate. This one only has one column, so it is simultaneously the leftmost and the rightmost. So it's the rightmost column. It'll be starts with half T's, half F's, and it also starts with T and alternates. Here, the rightmost column is the second one, and it starts with T and alternates. With the 8 rows, you got one in between, but while the leftmost one is half T's, half F's, the rightmost one starts with T and alternates. With 16 rows, yes, the leftmost one starts with half T's, half F's, but the rightmost one will start with T and alternate. Oh, it says my screen sharing is paused. So maybe you didn't see all that, but at least you could hear it. At least you could hear it. My screen sharing is paused. Oh, because you're looking at that. Oh, I see. Oh, maybe it's the whiteboard thing. This is interesting. Oh, look at that. Whoa. I'm experimenting. Yeah. In any case, we need 8. The reason why I took that tangent is because there are 1, 2, 3 atomic sentences or simple statements, and so we need 8 lines or 8 rows. And the pattern for the leftmost one is going to be half T's, half F's. So we're going to have 4 T's and 4 F's. Okay, and then this pattern will be the same here. If you can hear all the clicking. It's just taking kind of a while to register. All right, now the next column, the pattern looks like this: 2 T's, 2 F's, and then do it again. 2 T's, 2 F's, and then do it again. And then S is going to start with T and alternate. And so we could do that, but so it doesn't get too busy, I'm just going to go straight to not S, which is going to be the opposite of S. So if S is start with T and alternate, then not S is going to have to, well, and we could do S over here. Why not? So the S under here is going to be the same as the S here. So it's going to start with T and alternate. Oh, see, went too fast. T, F, T, F, T, F. That sounds funny too. T, F, T. It's almost like music. And so not S will be the opposite of this, which will be F, T, F, T, F, T, and so on. I'm going to make sure it's under that negation. F, F, T, F, T. It's like the Oompa Loompas. I'm making truth tables. What do you think? Okay. FT, FT, FT. This is getting sloppy. All right. Now what? Well, G, we got to copy all this down. It's referencing Willy Wonka. For those of you that are like, what is an Oompa Loompa and what is he saying? Is he humming? Is he singing? What's going on? Or Charlie and the Chocolate Factory is the book based on. Johnny Depp played Willy Wonka. Okay, 4 T's, 4 F's. And not L will just be L, but the opposite. So we'll have 2 F's, 2 T's, and then we'll do it again. I mean, this is supposed to be underneath this negation here, but it's kind of floating to the right. And I went kind of fast, so double check here. 2 F's, 2 T's, 2 F's, 2 T's, which is the opposite of this L, which is 2 T's, 2 F's, 2 T's, 2 F's, and 2 T's, 2 F's. Okay, S. T and alternates. This is the opposite. G is that pattern of 4 T's, 4 F's, 4 T's, 4 F's. All right. We're almost done. This is an and statement. So I'm just, a lot of times I'll just kind of start with what's the easiest. You could start here, start here. Oh, it's a main connective. So what's the main connective of this statement? Some of you might think, oh, it's this wedge. No, it can't be because that only applies within the parentheses here. Of course, this negation only applies to the S. So the main connective is the triple bar. The main connective here is the and or the dot, the conjunction, and of course, this is the main connective. So ands, they're only true when both parts are true. So it happens in line 1, line 3, and that looks like it's it, right? The rest of these are F's. So again, let's remind ourselves of what we are looking for. Well, the question asked us, can this person believe all of, does it make sense for them to believe all these things? So they're really asking, are these beliefs logically consistent, right? Because we want our beliefs to be logically consistent. So we have the truth here and the truth here. And gotta be very, very careful here. Sorry, this is true, and the rest are F's. This is F, this is supposed to be an F. See, when I'm talking, easily mess up. Okay. So we'll be looking for a line out of these 8 lines or 8 rows where all 3 of these statements are true. Okay. I think this is the next easiest one. So again, these are the truth values of not L. And if-then statements, horseshoe statements, they are usually true. They are only false when the antecedent is true and the consequent is false. And that happens in row or line 1, 2. And that's it. So the rest of these are T's. Believe it or not, a lot of truth. Yeah. So if-then statements, they are weaker than they might seem. I mean, it makes sense because they're based, it starts with a condition. Like, if you meet this condition, then this will happen. So it's not even, it's different than just, this is just saying if God exists, then so-and-so follows. That's a lot weaker than saying God exists, right? So look, if we want consistency, it looks like it's only going to be in row 3 because no other row has 2 T's going across. So we could jump right now to this spot. If we find a T, we need a T to be here, row 3. And to do that, we need to find the value. Why don't we just do all the values here? So this is a wedge statement, which is usually true. The only way that this is going to be false is when both parts are false, which happens in row 3, right? This is row 1, 2, 3. Both parts are false. This is getting very wavy, very wavy. Both parts are false here, happens here. And other than that, we're going to get a lot of truths, right? The truth will spread in a disjunction in an or statement. Okay, and so we can sort of, kind of ignore this now and ignore this now because we will be comparing these truth values. And with a triple bar, we are looking for sameness. So I see sameness in row 1 and row 2. Uh-oh, row 3. I do not see sameness. So we're going to get a false here. I get sameness in row 4. And it's not sameness in row 5 or row 6. But row 7 has both values are the same. They're both false. So we get a true here. D, and then we do not have sameness down here. Okay, so we are focusing on the truth values underneath the main connectives, which I'm ovaling. Is this ovaling or circling? Maybe it's the loose meaning of circling because this isn't a circle. And gosh, it's not even an oval. It's, enclosing, I guess. So are any of these 3 statements tautologies? No. To have tautologies, we would need all T's. We do not have that. Are any of them self-contradictions? No, we would need all F's in these columns. I'm kind of reviewing stuff from before. Are any pair of these two or these two or these two, are they logically equivalent? Well, they would have to have the same truth values. Well, the first and the second statement are not equivalent, and the first and the third aren't equivalent, and the second and the third are not equivalent. So we don't have any tautologies, we have no self-contradictions, we have no logical equivalency. By the way, all 3 statements are contingent because under the main connective, there's at least one T and at least one F, at least one T and at least one F, at least one T and at least one F. Okay, now, can this person, Eric Carson, does it make sense to believe all 3 of these simultaneously? Well, it just needs to be possible for all 3 of them to be true at the same time. They don't need to actually be true. They just need to be in some world. It could be in the actual world or some logically possible world. That's a world that can exist without contradiction. But there's only 8 worlds. There's only 8 possibilities given these truth functions. And look, in the first world, they can't all be true. In the second world, they can't all be true. In the third world, we got close. The second 2 are both true, but the first one isn't. In the fourth world, the first and the third are true, but not the second. In the fifth world, we don't have all of them true, and not in the 6th, 7th, or 8th. So these 3 statements are logically inconsistent, and if Carson claims that he believes all 3 of them, it doesn't make sense, and we can call him out on that. We want our belief systems to be consistent. We want the people in our lives to be consistent. We want them to make sense, especially like our leaders and politicians. If they say things that don't jive or mesh together, that's not good because we don't know what they mean, if they have this power and control, what exactly are they going to do with it? So that's good. So let's do new share. I want to share my desktop. So Eric here, is it possible that Eric's beliefs make sense? No. So that was 8 of, so was it 633? I think of 8 of 633. Eric's beliefs are inconsistent. Therefore, they do not make sense. Awesome. Awesome, awesome, awesome. So we classified statements. We learned how to compare them. We know about consistency and inconsistency. And so all we have left is to use truth tables for possibly their most powerful. This is the most powerful thing we can do with them, is use them to determine validity of deductive arguments. And this shouldn't be too bad, given that we have already we've done some serious truth tables. We just did an 8-row truth table, and then after that we will look at a faster way to do these truth tables. We've done a lot, so I'm going to pause there. So thanks for hanging out, those of you who did listen to me humming, and I'll see you next time.